okay, to different things in and out the cells. Okay, we're talking about diffusion. Okay, simple diffusion that occurs freely across the membrane when the substances don't have any charge, okay, from high to low concentration. Then there are other substances that need a transporter. For example, glucose, ions that have a charge, okay, are gonna pass through facilitated diffusion. Okay, the simple diffusion, when you increase the concentration of a substance, okay, that will increase the rate of diffusion, and the more you increase the concentration, the greater will be the rate. In theory, without any limit, okay, makes this line that has no plateau. Now, when you depend on transporters, there will be a limit. Okay, if simple example is you are in a supermarket, you have 4 or 5 people in the registers. If they are busy, there is nothing you can do. You have to wait in line. Doesn't matter that the line is 1 person, 5 or 20 persons, they have their rate. When they finish with one client, they are gonna take the other. Okay? At the beginning, when they are doing, if you go when the supermarket opens and they are not, they don't have any client, the clients go one by one, as they go out. But once they are busy, everybody else has to wait. The same thing happens with these substances that require a transport. Okay, ions, sugars, amino acids. When we start increasing the concentration, the rate of diffusion or facilitated diffusion increases. Once all of the transporters are occupied, everybody else has to wait. Okay, that's why this line reaches a plateau here, which is called the Vmax, which is going to be different for every substance, and also for medications that have to be absorbed, secreted. Okay, when you study pharmacology, you are going to see the importance of this Vmax that we have to have in consideration when we give patients different medications. If they are healthy, we give a dose. If they have a kidney failure, we give a lower dose, okay, because of these differences in the rate of excretion, absorption, etc. So there are many ways that the membrane has to let things pass. For example, there are pores in the membranes. For example, in the nucleus, you remember there are pores that allow the RNA to move out for the synthesis of proteins, also exchange of ions, water, etc. Some important pores are the aquaporins. Okay, they are present in the cells to allow the pass of water. Okay, the exchange of water, so the cells can regulate their volume. Later we are going to be talking about tonicity, about osmolarity. We're going to see how the cells regulate their volume by allowing more or less aquaporins to be open. Okay. Important aquaporins are present in the kidneys and GI tract cells. Okay, that one of the most important functions of the kidneys is to retain water if we need it. If we don't need water, if we have excess water, we are going to let the water go out. Okay, we are going to learn a lot about this when we study the renal system. Okay, remember the nephron has in the last part the distal convoluted tubule, the collecting ducts. Okay, the cells in the collecting duct, let's imagine this is a cell in the collecting duct. They normally have the aquaporins, let's call them AP, in the cytoplasm. They are not present in the cell membrane. Okay, if we are drinking enough water, these aquaporins are going to remain there because we don't need to retain that water. Now, if we are dehydrated, know that something that happens is the release of antidiuretic hormone, okay, from the posterior pituitary. This antidiuretic hormone will bind to this cell membrane and will activate several mechanisms to place the aquaporins in the cell membrane. Okay, so they start retaining water. Okay, so some cells have these aquaporins permanently there. Other cells can have them present or not in the plasma membrane. Now, channels is an important topic in physiology. It is important to understand how cells regulate how much sodium, potassium, calcium, and other ions that they let in or out. There are many channels. Okay, some channels are constantly open. They are called leaky channels because they allow the free exchange of sodium, potassium. So the sodium-potassium pump then redistributes these ions. But some of these channels have gates. They are called gate channels. And they are specific for certain ions like sodium, potassium, calcium, chloride. Extremely important this topic for pharmacology and pathophysiology. You have heard about different medications that block these channels, calcium channel blockers. Okay, for example, other medications block the potassium channels, block the sodium channels. Okay, so understanding the physiology of these channels is essential for the pharmacology and pathophysiology. Now, these channels can be in different positions or different states. They can be open, they can be closed, or they can be inactive. Okay? One way of representing that I've seen is you can use your hand. Okay, you close your fingers and you put the thumb on top. This is a closed channel. Okay, nothing can pass through. When you open your hand, that is an open channel. Anything can pass. Now, what is an inactive channel? You close your hand with the thumb inside. Okay, it's more difficult to open. Okay, because your fingers are holding the thumb. Okay, that is a way of representing what is an inactive channel. They can be represented in this way. Okay, let's imagine this is a channel. Okay, or this is a cylindrical structure with an opening inside, and they have two gates. The gate A and the gate B. This is the way they are normally present in the cell membrane. They are integral proteins that are present in our cell membranes. Let's imagine this is a channel that only allows sodium to pass, specific for sodium. Okay? When necessary, when a stimulus activates this channel, this gate number, the gate A is going to open and sodium is going to enter because there is a high concentration of sodium here and a very low concentration of sodium inside the cell. Okay, so sodium starts coming in, okay? But there is a moment when the electrical potential of this membrane will change and this will produce the closure of the gate B. Okay, this gate can be open, but the channel, the gate B is going to be closed, and this will inactivate this channel. So if someone tries to stimulate again the opening of this gate, nothing is going to happen because it's blocked. It's inactive. Okay, we are going to see this later when we study the membrane potentials to see this in action, to see how it works.
Right, so based on the drawing there, when you activate gate A, then gate B closes?
No. Okay, no. Listen, here is the explanation. When they are open, they are going to be open to both sides of the membrane. Okay? So letting everything pass. There has to be a specific membrane potential for this to close. So this, imagine you got a stimulus here. This opens, sodium starts entering, you are increasing the positive charges inside the membrane. This membrane will start increasing the membrane potential, okay? And once it reaches a level, this will close. So nothing else happens. We're gonna see this in action later. They have gates, okay? These gates can inactivate the gate B, the channels, making them useless. So nothing else can happen through this channel. Okay, they will respond to stimuli, different stimuli. For example, the binding of a neurotransmitter. It's a chemical substance. These are called chemically gated channels, or changes in the membrane potential. Okay, these are voltage gated channels. Or sometimes they open when you stretch the cells. Very important for the regulation of the blood pressure and the blood flow to different organs. Okay, if suddenly a lot of blood enters into an organ, the blood vessels will dilate. We are going to stretch the walls of these blood vessels. This will open the channels, okay? Mechanically gated channels. This is what I was representing there. Okay, there are two gates. One is called the selectivity filter. Only sodium, only potassium, only chloride, only magnesium, calcium, etc. will be able to pass. And this is the other gate. Okay, that is the one that can inactivate these channels. Well, carrier transporters or carriers, another form of transport. Carrier-mediated transport moves ions and organic solutes passively across the membranes. Okay, carrier proteins, this is a difference with these gated channels. Remember, when they are open to both sides. The carriers are never open to both sides of the membrane at the same time. Okay? They are specific for certain things. When this specific thing binds to them, they are going to change the configuration to allow this substance to pass. Okay? These have also two gates, but when one is open, the other is closed. Okay? This is a difference between these and the gates. Okay? They allow very fast transport. Polar molecules, they reach saturation. That means when they are busy, nothing else can pass. Specificity, okay? Only certain things are able to pass. And this is very important. They have what we call competitive inhibition. Okay? If there is a molecule that is similar in chemical structure, okay, that channel will prefer that other molecule if the concentration of that molecule is higher than the concentration of the molecule that it normally lets. Okay, let's say this is a carrier. This protein here is a carrier that normally allows the substance A to pass. Substance A binds, that produces a change in the configuration, and substance A goes inside the cells. Okay, let's say this substance now is in a concentration of 10 milligrams per deciliter of blood. This is working, okay. If you increase the concentration, the rate will increase until it gets saturated. Okay, but let's say now I want to stop A from entering into the cells. So I'm gonna give the patient a substance that I'm gonna call B, and it's gonna be at a concentration of 100 milligrams per deciliter. So, since substance B is very similar to substance A, this channel, or this carrier, sorry, is gonna prefer B rather than A. It's gonna stop taking A and it will start taking B. Essential to understand the function or the mechanisms of some medications or poisons. The same happens with poisons. Okay, substances that look similar to our proteins or our chemicals, so our cells stop taking what they normally take and start taking the poison or the drug inside. And of course the movement, as in all types of diffusion, okay, passive diffusion will depend on the concentration gradient. Yes?
What's the difference between like a carrier-mediated transport and an enzyme? Because it sounds to me almost exactly like an enzyme.
Also, this competitive inhibition also applies to enzymes. An enzyme is working with this substance. If you increase another, if they have competitive inhibition, okay, they will take the other one instead of this. Okay. And that happens, for example, one typical example is poisonous alcohols. Okay, we have an enzyme in the liver that is called alcohol dehydrogenase that normally transforms, is working with alcohol, ethanol. Okay, if we take methanol, that enzyme is going to start metabolizing methanol, which is a poisonous alcohol, and making toxic substances, which are the ones that kill our body. So what is the treatment? Give ethanol. Okay, they normally works with processing methanol. So you increase the amount of ethanol in the blood, you actually make the patient drunk, and you have to keep them drunk, so the alcohol dehydrogenase doesn't process methanol and works with ethanol.
So it basically prioritizes the other molecule to maintain equilibrium.
Prioritizes the one that is in higher concentration.
Yeah, so we get equilibrium.
And this is a treatment that is off-label. Okay? They actually have to go to a supermarket, to a liquor store and buy vodka and give vodka to the patient. There is no pharmaceutical preparation to give IV ethanol, or they have to go buy the alcohol and give it to the patient so the patient drinks the alcohol and keep them drunk so they don't die, at least of the methanol. Okay? That's very interesting. So competitive inhibition is a very important concept to understand many of the mechanisms of action of medications. Yeah, carriers, enzymes. The difference between the enzyme and the carrier is simply that the carrier is in the cell membrane, and the enzyme is in the cytoplasm or in the nucleus or somewhere else, working inside the cell. But they are proteins. They are proteins that are doing a job. Here we have the transporters, these carrier proteins. Okay, notice there is a high concentration of this substance outside the cells. Notice how the carrier is not open to both sides. You have one of these substances bound here. There is a change in the configuration of the protein, change the shape. So now it closes to the outside to release the substance to the inside. Once the substance is liberated, the protein moves back to this position, takes another, releases inside, moves back to this, okay, goes from A to B, until there is an equilibrium, okay, between in the concentration of this substance inside and outside the cell.
So is that the same like the sodium potassium pump or no?
No, this is a type of passive transport that doesn't require energy. Okay, there is no ATP involved in this. Goes from high to low until equilibrium is reached. Pumps, imagine you have to move this substance from here to there. Okay? There is high concentration here, low concentration here. So it's impossible to move it because of the concentration. You use ATP to pump the substance from low to high concentration up the hill. Okay? Yes.
Also, competitive inhibition, would that occur with lipids as well?
With lipids, remember these are four proteins or ions, glucose, amino acids, ions. Okay, lipids normally are non-polar substances that pass freely across the membranes. Okay? They don't need transporters of this
I was
type.
thinking about HDL and ADL or something.
HDL, what HDL stands for?
High density lipoprotein.
High density lipo, what? Protein. Proteins are polar substances. They have some lipids. Okay, these lipoproteins are transporters in the blood of lipids. Okay, lipids are not water soluble. So you can't transport a lipid alone in the blood because it's not water soluble. You have to bind it to a carrier protein like steroid hormones. Testosterone, okay, all of these steroid hormones have to travel bound to a protein. Okay, that's why you are gonna measure the amount of the carrier proteins in the blood. For example, free testosterone versus bound testosterone to the transporters. Okay, remember here, it's easy to get sometimes confused because we are talking about the transport. Transport where? Okay, remember we are talking about transport across the cell membrane. Moving things from here to here. Okay. Different things transport in the blood. Okay, these things are produced, for example, cholesterol goes from the liver, or triglycerides go from the liver to the periphery, or the other way around. Hormones go from the endocrine glands to different targets. They are going to be transported in the blood. in the plasma, okay, freely floating in the plasma. Here is across the membrane, from the outside to the inside of the cell. Now, active transport is a very important type of transport, thanks to which we are all alive. It's the one that maintains the steady states in our tissues, in our cells. And this is the one that requires energy. Okay, we are going to study two types of active transport, primary and secondary active transport. Okay, that are the ones who help us reach the steady state, and also the uptake of certain substances like amino acids, glucose, medications. Okay, this is made by integral membrane proteins that use ATP to pump things from low concentration to high concentration. Okay, think, for example, in the ATPase, sodium potassium ATPase, that has to take the potassium from outside the cell, where there is a very low concentration, to inside the cell and push the sodium out against the concentration gradient. We are going to see the example of this, for example, in the muscle contraction. In the muscles, we have the endoplasmic reticulum contains lots of calcium. When the muscle contraction is going to occur, calcium is released a little bit, okay, to initiate the muscle contraction, but then to relax the muscle, you need to take the calcium from the sarcoplasm into the sarcoplasmic reticulum again. So from low to high concentration, there is a calcium pump. Okay. The proton pump that we have in the stomach has to pump ions, hydrogen ions, okay, from low concentration inside the cells to high concentration in the lumen of the stomach. Okay, so when you need to push things against the concentration gradient, you need to use ATP. There are other pumps, for example, something that is called the ATP binding cassette, ADC. That is very important for nutrient uptake, for cholesterol and lipid trafficking, resistance to cytotoxic drugs and antibiotics. Okay, a cytotoxic drug is trying to enter the cell. So there is a high concentration of the cytotoxic outside the cell, a little bit inside the cell, and the cells push the drugs outside. I don't want this, I don't want this. When they develop this mechanism, this creates resistance to treatments. Take chemotherapy, antibiotics. This ABC is also important in immunity, stem cells, etc. We are going to be talking a little bit about these in future lectures, okay, to understand the importance of the ATP binding cassette. Now there is also secondary mechanisms of transport. Okay, these don't use ATP directly. We're going to see a diagram later. But they require of a working sodium potassium ATPase for them to work. Okay, there are several examples in our body. Okay, for example, we depend on this secondary active transport for the uptake of amino acids and glucose. Okay, we're going to see later this in the diagram. They don't use ATP, but they use the electrochemical gradient that is created by a pump that is located in other parts of the cell. Okay, the sodium potassium pump. Okay, they have exactly the same characteristics, okay, that other transporters have, specific. They reach saturation, competitive inhibition, like the passive carrier-mediated systems. One important thing is that they don't function in the absence of the ion that drives their force. Okay, the ion that moves along the electrochemical gradient and supplies the energy. They depend on this electrochemical energy, okay, to transport solutes against the concentration gradient. And there are two types. There are importers and there are antiporters that I'm sure you have seen in the past. Importers simply pass two substances in the same direction. Antiporters move one to the inside of the cell and the other to the outside of the cells. This diagram represents this. Okay, notice that here in the upper left part, we have the sodium-potassium pump. Okay, it uses ATP. Notice that ATP is only present here. Okay, hydrolyzes, breaks down the ATP into ADP, adenosine diphosphate, and free phosphate. Okay, it's taking sodium out and potassium inside the cell as usual. Now here, in the upper right part, we have a symporter. This symporter is an example of a secondary active transport. Okay, this X can represent, for example, glucose, or can represent amino acids. Let's imagine we are in the gut. Okay, we are eating, we take something that contains sugar, a piece of bread, and we take some meat or fish that has amino acids in it. For the absorption of this glucose, we need the amino acids. And for the absorption of the amino acids, we need the glucose. They have to be absorbed together. Okay? And they need the driving force of the sodium-potassium pump. That is doing what? Reducing the concentration of sodium inside the cells as much as possible. When you have a very low concentration of sodium inside, then you can take sodium from the outside through this symporter. Once sodium and glucose or amino acids are there, this protein is going to enter both of them only if the concentration of sodium here is very low. That is the electrochemical gradient that the sodium-potassium pump is creating here. So now the substance X, what will happen? Substance X will use other types of transporters. Once the concentration of X is very high here and is low here, X will leave the cells. In this case, to the blood.
To the where?
To the blood.
So kind of osmotic process.
Kind of.
Osmotic process.
Osmosis is forward. This is simple diffusion, or facilitated diffusion in the case of amino acids. So let's imagine that here we have a channel that is specific for amino acids or for glucose, okay, of the facilitated transport type that we mentioned before. If the concentration of X is higher inside the cells than in the interstitial space here, these transporters will allow X to move out. Okay? It will go through the blood to other places, so the concentration of X here is going to be low always. And we absorb X. And here we have an antiporter. Okay? Notice how sodium moves in, it's taken out, it's going to be taken out by the ATPase to be exchanged by other substance. Okay, we are going to see examples of this in the kidney physiology. Okay, this is just understanding the concepts. So when we go to the kidney, we go to the GI tract, you already know, okay, this is the antiporter, this is the symporter. Now I understand how we reabsorb this, how we excrete that. Okay, why sometimes we absorb, sometimes we secrete substances, because it will depend on the functioning of these symporters, antiporters. There you have some examples of symporters. Okay, sodium sugar transport system, sodium amino acid symporter that we use to absorb amino acids and glucose. Then we have the sodium chloride co-transporter that appears in the distal tubule. Example of the importance of this for pharmacology. Okay, this is inhibited by thiazides, which is a diuretic. This thing is reabsorbing sodium chloride, so we don't lose salt. We maintain our sodium in the blood. We keep our blood pressure. But if this is too high, we inhibit this protein, so it doesn't reabsorb more sodium chloride. We let the sodium escape, water goes out, and blood pressure drops. Antiporters, there you have examples. Sodium, hydrogen exchange system, sodium calcium exchange system that we are going to be studying in the future. And there you have more examples, by the way. Here is a link. Is anybody having troubles with the links in the PowerPoint?
I am.
1, 2, 3, 4.
But I think they may have to do with the fact that my computer says that I have to buy the PowerPoint. And I think I've just got,
Did you download the PowerPoint or you're watching it in the,
I'm watching it.
and it doesn't work? But works for some and doesn't work for others.
You just have to double click and press open hyperlink. Yeah, you have to like it copy the hyperlink and paste the drive. That's what I just did. Just copy the hyperlink and you paste it on your browser.
But for me it's working. I just click there. I can delete that and upload it again. Okay. Can you try please with the second PowerPoint that I uploaded to see if the same happens? There you have more things today about these transporters. Okay, there you have some examples. Okay, let's take a 10-minute break. Let's meet at in 10 minutes, 11:22. Okay. Okay, the most important example to learn about these transporters, these transcellular transport systems that we have been mentioning. Transcellular transport is simply when we move a substance from one side, let's say you have an epithelial layer, and you have to move it to the other side. Okay? Up to now we were talking about how we transport things from point A to point B, or from point B to point C, across the membrane. Okay? Now we are going to talk about how we transport substances from point A to point C, transcellular mechanisms of transport. Okay? We have gates in the cells. Some of them are located here in what we call the apical part of the cells, the one that is looking at the lumen of, for example, the intestine or the kidney tubules or the blood vessels, okay, any epithelial layer. And we have the basolateral membrane, which is the one that is looking to the blood side. Okay, notice how we have here on the top part of the cells the tight junctions that make sure that nothing passes through in between the cells. There are exceptions that we are going to see in the future, but most things can pass. For example, a bacteria around there won't pass through the tight junctions. Okay, some diseases, you're going to see that have a destruction of the tight junctions, so these epithelial cells separate and bacteria pass. Okay, we're going to see examples. Now, there are different mechanisms to make these substances to be absorbed, or sometimes secreted. Okay, you can pass substances from here to here or from here to there, depending on what you need. One of the most important examples is this sodium glucose cotransporter and the sodium amino acid cotransporter, which are symporters that act as secondary active transport mechanisms for the absorption of glucose. In this case, glucose will enter. Remember, this is driven by the energy, electrochemical energy that the sodium-potassium pump creates. Okay, low concentration of sodium inside the cells, or is sodium going out. And what about the glucose? Once the concentration of glucose is very high here, we have transporters to move the glucose to the blood. Okay, GLUT2 transporters. There are several examples that we are going to be studying. And in the case of the amino acids, there are also specific transporters in the basolateral membrane of the cell. It's the same mechanism using different transporters. Yes?
So the first part will be important.
The first part is a syn-porter, secondary active transport mechanism. Here you have the primary active transport mechanism, and this is simply facilitated diffusion. Okay? What happens if you, for example, increase the glucose concentration here for any reason that normally is not supposed to happen because the blood is moving? Now, this transporter is not going to work. Once the concentration of sugar here is very high, it will increase inside the cell and it will stop the syn-porter and the process stops. Okay? But this is normally working perfectly well. So this happens also for several medications. Okay? This is the way we have to absorb medications. Now we are going to talk about water, which is the osmosis thing. Okay? Osmosis is a type of transport that works for water and is a mechanism that allows the cells to regulate their volume. Okay? Cells need to have a perfect volume, shape, and everything in order to work. Spontaneous movement of water across membrane, okay, that tends to equalize the concentration of solutes on both sides of the membrane. Okay, for example, I have represented here a cell. I put some numbers, which is the approximate osmolarity of the extracellular and intracellular fluid. Okay, this is not the exact value, it's 280, but we're going to work with this 300 to make it simple. Cells are always trying to maintain this osmolarity equal at both sides of the membrane. They are going to do whatever they can. They have several mechanisms. If now the surroundings have increased osmolarity, let's say we eat a pepperoni pizza, and this increases from 300 to 400, they are going to use some mechanisms so they don't suffer. Okay, most of our cells have these mechanisms for short-term adaptation, except the red blood cells. Red blood cells don't have these mechanisms. That's why they are so sensitive to changes in osmolarity. Okay, erythrocytes don't have these. Okay, so we depend on our body, our endocrine system, nervous system, maintaining the blood osmolarity for the red blood cells not to be destroyed. Now, when we have two solutions, for example, the ones that I represented there with the same osmolarity, or osmotic pressure, which is the pressure that drives this water, we say that they are isoosmotic, same osmolarity. Okay, if they have a higher osmolarity, if one of them has a higher osmolarity, it's going to be considered hyperosmotic. Okay, let's say the example I gave you before, we drink water that contains salt, we eat fried potatoes or pepperoni, etc., the osmolarity of the extracellular fluid will increase. And if we have a solution that has lower osmolarity, that is going to be called hypoosmotic. Okay, and you have studied before what happens when cells are placed in hyper or hypoosmotic solutions. But we have to understand also a concept that is related but is not the same to osmolarity, and this is tonicity. Tonicity is probably more important than osmolarity. Okay, when we calculate the osmolarity of a solution, we simply take the concentration of all of the solutes, sugar, sodium, potassium, chloride, and we add them up, and we obtain a total, which is the osmolarity. Now, when we talk about tonicity, we don't calculate all the solutes. We are going to calculate only the ones that don't enter into the cell easily. For example, sodium. Sodium, remember, is going to be pushed out. It's not very easy for sodium to enter into a cell. So that is the most important solute that determines the tonicity of a solution. And the tonicity is the one that determines the volume of the cells. Okay, sodium is the most important of the ones that we call effective osmoles, because it doesn't penetrate. But there are other solutes, for example, urea, dextrose, which are called ineffective osmoles because they enter into the cells by different mechanisms. Okay, so for example, if you add 100 milliosmoles of glucose here, this solution now has 400 milliosmoles. Okay, this is a hyperosmolar solution. What will happen? Glucose is going to start entering inside the cells. And there is a moment when the amount of glucose outside and inside the cell is going to be the same. So this is not considered a hypertonic solution. But if we add 100 milliosmoles of sodium, now sodium is not going to enter. It's effective osmole. So this solution that contains sodium is hyperosmolar and also hypertonic. And what will happen? Well, we have aquaporins here. What will happen with the water that is inside the cells when you have a hypertonic solution outside? Sodium is gonna, water is gonna move out, and the cells are gonna shrink. This happens to the red blood cells mostly. Our cells have different mechanisms to cope with this. And this is the reason why, for example, when imagine someone is dehydrated. The blood pressure is going down. Okay? Very low blood pressure. Imagine that I give this person an intravenous solution of dextrose 5%. This person here, does it work? This person is dehydrated, blood pressure is low. I give dextrose 5%. It's water and glucose. Okay, at the beginning I'm increasing a little bit the osmolarity of this part. Okay, so maybe some water will try to move out, but since glucose is going to be taken by the cells, glucose is going to enter, the osmolarity is going to be the same, and water will enter from the extracellular to the intracellular compartment. This water is going to be distributed among the intracellular and extracellular compartments. If you give 1 liter of dextrose 5%, 2/3 of it is going to enter inside the cells, because remember, our intracellular compartment is 2/3 or contains 2/3 of the body water. So the blood pressure is not going to be modified at all. I'm going to even damage this person because I'm producing a swelling in the cells by giving extra water. So instead of 1 liter of dextrose 5%, I'm going to give normal saline, which contains sodium chloride, 0.9% of sodium chloride. That way I increase the osmolarity of the extracellular fluid. Since sodium doesn't enter into the cells, the water is going to remain here. It's not going to take water from the cells because this solution has exactly the same osmolarity of the plasma. So that water, that liter of water, is going to remain in the extracellular compartment, increasing the blood pressure. Okay, that's why we give normal saline to patients who are dehydrated, and we don't give dextrose 5%. Okay, we could even kill someone by giving dextrose 5% when they are dehydrated or they have hypotension. So there you have examples. Okay, hyposmotic solutions, isosmotic solutions, 0.3 milliosmol, which is 300 milliosmoles, 0.3 osmol, which is 300 milliosmoles. Okay, what happens when they are in a hypotonic solution? Simply, the water will enter into the cells, okay, following these osmosis mechanisms, and the cells are going to swell and burst. This is a classic picture that I'm sure you have seen many times, okay, of what happens to these cells in different situations. Now, there are some regulatory mechanisms that we mentioned before. Okay, for example, some cells adapt when they are placed in a hypotonic solution. they can start taking potassium out and amino acids out, trying to maintain their volume. The red blood cells can't do that. They don't have the mechanisms to do this. On the contrary, if they're in a hypertonic solution, they can take sodium inside the cells, okay, to increase the volume. These mechanisms work if the conditions are maintained in a short term. Okay, there is no way a cell can survive for a very long time by taking sodium to maintain the volume or by eliminating potassium or amino acids. This in the short term works. Some cells have developed long-term adaptations when they are exposed to hypertonic solutions for a long time. Think in the kidney. The medulla of the kidney, you have seen pictures of the kidneys. When you open them, the medulla is very dark compared to the cortex. This medulla is dark because it has a lot of sodium chloride. Okay? It has a lot of salt, which helps in the reabsorption of water. The cells that are placed there have developed these long-term adaptations. They, for example, produce substances that don't interfere with the metabolic activity. Okay, so they maintain a very high osmolarity inside that is the same that the interstitial fluid outside. For example, sorbitol. Cells in the kidney medulla produce sorbitol and have this sorbitol inside, so they can cope with this very high osmolarity. And they maintain their volume in the presence of this hypertonic extracellular fluid. Yes.
I have a question on the previous slide.
Here?
So you said it's not common that sodium enters the cell, right?
No, not at
But-
all. But enters, but it's taken out.
Yeah. So that, the second bullet point, that only is referring to blood cells, red blood cells?
No, except red blood cells.
So that does not happen.
Most of our cells have these mechanisms. When the osmolarity of the blood, you are taking something that contains lots of salt. You are temporarily increasing your blood osmolarity. Our cells don't suffer because they start using these mechanisms. Okay? But normally you drink water after you eat, or your third mechanism is activated and you will drink water at some point. Okay? The red blood cells don't have these mechanisms. They are going to swell a little bit, they are going to shrink a little bit, they are very flexible. Okay? There has to be a really, really elevated osmolarity in the plasma for them to swell or burst or shrink. This is just temporary, okay? Just in the short term. Well, the last topic of this first section is to study what is the resting membrane potential, which is very important to later understand different types of electrical potentials that occur in the cells, in the neurons and in other cells. Remember, our cells are maintained in a steady state, okay? Sodium low and constant inside the cells, potassium high and constant outside the cells. Also understand that cells have channels, leaky channels that allow some sodium to enter, potassium to leak out. Sodium-potassium pump reestablishes this steady state using ATP. Potassium is exiting, the rate of exit matches the rate of active transport. This is something that is working constantly in our cells. The ATPase normally takes or exchanges 2 potassiums, okay, for 3 sodiums using 1 molecule of ATP. This is the basis of life as we know it. Okay. Just a reminder of what is the steady state and how it works. Now, to maintain this steady state, okay, is the basis of what we call the resting membrane potential, which is simply the difference in electric charges across the plasma membrane when the cells are at rest. cells are not being stimulated. Okay? And when we study this, sometimes I imagine that we think that cells spend many hours with this resting membrane potential, and then suddenly cells are constantly moving between this resting and the excited state. Some of them with a higher frequency, some of them with a lower frequency. But most of our cells are constantly doing something. Okay? Sometimes very low activity, sometimes very high activity, sometimes this activity changes from one part to another, but they are constantly working. There you have this representation of the sodium and potassium channels, passive exit of sodium and potassium, and the ATPase re-establishing the potential.
So at all times, like you said, potassium just leading to the to the non-gated channels.
You have leaky channels, okay? Potassium out, sodium in, and the sodium potassium pump maintaining this using one ATP that you see there. Now, we saw a video in the last lecture about the electrochemical gradient. Yeah, remember these videos? If they are short and you have time, try to watch them several times. It's the only way that we can keep these ideas in our minds. Okay? The difference in electrochemical potential is what drives the movement of the ions. Okay, you have here again the concepts of the movement from high to low concentration. Okay, electrical charges, they are the same, they repel. When they are different, they attract each other. So positive ions will look for negative charges, and negative charges for positive charges. Okay, if you add all of these driving forces, the chemical and the electrical, you are going to have what is called this gradient or electrochemical gradient that will be specific for different solutes. Remember the video we saw how this happens for potassium. You open the potassium channels. The potassium will start leaking out because of the high concentration inside the cells. Once you have enough potassium outside, which is positive, the amount of potassium that exits the cells is going to be decreasing, and this potassium that is out is going to feel attracted by the negative charges that were left behind. So there is a moment when there is going to be an equilibrium. No more net exit or entry of potassium. If you measure the electricity or the potential at that point, it's going to be a negative value, which is specific for potassium. Okay, and if you do the same for sodium, imagine you open only the sodium channels. Lots of sodium will start going inside the cells. So the positive charges are going to accumulate inside. There is a moment when an equilibrium will be established. If you measure the membrane potential at that point, you're going to obtain another number, which is a positive one, okay, which is called the equilibrium potential for sodium. Every ion will have its specific membrane equilibrium potential. Yes?
Professor, it's an equilibrium based on the steady state, right? Equilibrium that the cell needs
The
to have.
movement of the ion reaches an equilibrium, and we say that because there is no net movement in and out. We call that equilibrium potential for that ion. Now, when you take all of these little equilibrium potentials that are maintained by the action of the sodium-potassium pump and the integrity of the membrane, is when you develop what is called the steady state, which is the difference of high potassium inside the cell and high sodium outside the cells. Okay, these are little equilibrium mechanisms that exist, okay, that all of them contribute to the establishment of these steady state in the cells. There you have the 1,4 potassium minus 90. Of course, nobody please memorize these numbers, because this will depend on how many potassium channels the cells have. So this will be different for every cell in the body. We are just giving a number, okay, which could be considered an average, okay, for this. Who was going to ask?
Is this the same driving force that's like for action potentials in nerve cells?
We are going to enter in the action potential later, okay, in the next
But
lecture.
it's the same concept.
This is essential to understand for understanding later the action potential. Okay, why membranes develop this resting membrane potential? This is only for potassium. Okay, then you have the one for sodium, the one for chloride, for other ions. When you balance all of those forces that are occurring in the membrane at the same time, you will obtain a value that is a resting membrane potential.
And what was the main difference, again, between equilibrium and the steady state?
Okay, equilibrium is, for example, you have two compartments. You put a solution here. By different mechanisms, it will diffuse or will be transported to the other side once you have the same concentration here and here, and the same amount that moves there comes back, you have a zero net movement of that substance between the two compartments, the same substance. You have an equilibrium. When you put ink in water, it will diffuse, and there is a moment when everything will be homogeneous. Now, steady state is when you maintain a different concentration of two solutes between two compartments. And there is no net movement of one. Let's say the membrane is here, I am sodium, potassium is there. Sodium goes out, sodium moves out, and moves in. The same is doing potassium there. We are in a steady state. Now, if someone drinks a poison or has no oxygen and the sodium potassium pump stops, potassium, sodium is going to start leaking out freely. Potassium is going to go that way, and there is a moment when you're going to have the same concentration of sodium and potassium everywhere. So we don't want to be in equilibrium. We prefer to be in the steady state. Okay? There you have the equilibrium potential for potassium. Remember, will be a -1, positive charges leaking out. There you have the one for sodium, which will be positive because there are positive charges going inside the cells. And this is the one that is going to be taken out by the sodium potassium pump, because we don't want the cells to reach that value. Okay, we need to maintain what is called the resting membrane potential. Different ions will have different equilibrium potentials. This is specific for every ion. Now, the resting membrane potential is when you add all of these forces, okay, the effect that all of these equilibrium potentials make together, okay, is the electrical potential difference across the plasma membrane of normal cells in the unstimulated state. These little seconds that they are unstimulated. We can measure that simply by placing an electrode inside the cell membrane, one outside and one inside. It's going to measure the difference in charges between the extracellular and intracellular compartment. Okay, this will be determined, what are the main determinants of this membrane potential, by the ions that can cross the membrane and are prevented from attaining equilibrium by the sodium-potassium pump. That means if the sodium-potassium pump stops, you are not going to have any difference. Okay, remember what is a potential? What is potential energy? If you drop this there, that is kinetic energy. But if it's heavy enough, it's going to break this surface. This has energy. If I hold it here, potential energy is able to do something. If I have $1 million in my bank account, I have the potential to buy a beautiful house. Right? I don't have the $1 million. I don't have this potential energy. Okay. Potential energy. Once the potential energy is going to be transformed into kinetic energy that will do a work. It's the capacity to do a work, the potential energy that the membrane has. If there is no difference between the two sides of the membrane, the potential energy is zero. So the membrane can't do anything. So my brain wants to stimulate my diaphragm to contract. can't. Because there is no way that you can transmit electricity in a system in which there is no difference, or in which there is no potential energy. That's the reason of life.
Professor,
Yes.
I have a question about the previous slide.
Mhm.
When it comes to the polarity of each
Yes.
side, and what comprises that polarity, and I know it's ever changing,
We are
but,
gonna get there.
okay.
That's for the action
because
potential.
I'm not that much of a nerd, but
We are
I
gonna get there.
definitely couldn't figure that out.
Okay, so these are examples: sodium, potassium chloride. Okay, are the most important ones that contribute to this potential. Now remember, every ion will contribute in a different way depending on how many channels the cell has. That's why I told you, don't get married with the numbers, because cells that have more potassium channels will let more potassium out. Cells that have more sodium channels will let more sodium in. So the equilibrium potential will vary and the resting membrane potential will vary. Okay, what is the particular permeability for that particular ion? If there is a higher permeability, okay, that will contribute more to the specific membrane potential of that cell. Okay, normally the plasma membrane of most cells has higher permeability to potassium than to any other ion. And that's the reason why in most of our cells, our resting membrane potential is close, not equal, but closer to the equilibrium potential for potassium. And if we go back, we are going to see that it's around minus 90. Some cells will have minus 70, minus 75, okay, minus 60, minus 100, depending on that specific cell. The numbers that you have learned in the past are just simple examples. Okay, it's written this way in the books to make easier the understanding, but this is totally different for different cells.
Yes.
Yeah. That's you and that's me as well. Don't think that this is easy. Yes.
Professor, and we only consider that for sodium and potassium?
Sorry?
Membrane potential, we only study that in sodium and potassium?
Well, you can put everything together. I put there a link to this nearest equation that you have this diagram that you can play with different ions. I don't recommend it because it can be very confusing. Okay, but we are going to focus on potassium, sodium, mainly to understand what happens, for example, when, let's go back. I am potassium. There is a concentration of potassium inside the cell and a little concentration outside. You open the channel, I move freely. But what happens if this guy starts eating 2 pounds of bananas and there is a lot of potassium outside? Now, there are a lot of positive charges there. For me, it's very hard to go out. Okay? These are the things that we have to start understanding. What happens to the resting membrane potential when you have higher potassium than normal outside? You have a lot of positive charges, so now probably potassium will try to come in. So what happens? You will have more positive charges inside the cell, so the resting membrane potential that was 60, minus 60, now goes to minus 65. So what happens if you want to stimulate the cell? It's going to take longer to stimulate the cell. Okay? Besides, having this very low voltage inside the cells can also inactivate some sodium channels. So now, even if you stimulate the cell, they don't open. And then there is when you start having trouble. That's the reason why we have to keep these values as close as normal as we can.
Would that also be affected by like other things like anions or other proteins you could turn around the cell? That wouldn't be sodium or potassium?
Yeah, every ion. Okay. Either if you have hypernatremia, hyponatremia, hyperkalemia, hypokalemia, they will have an effect in the resting membrane potential. They will either depolarize or hyperpolarize the cells. gonna talk about the action potential. You have the resting membrane potential here and a threshold. Stimulus comes, if it reaches threshold, it's gonna generate an action potential. If it doesn't, so let's imagine this is a neuron. Threshold and resting membrane potential. If you have a hyperpolarized neuron, you need a really high stimulus for the neuron to reach threshold. And if you have a depolarized neuron, the minimum stimulus will create an action potential. Sometimes you're going to have paralysis, sometimes you're going to have weak chest, you're going to have spasms, you're going to have different things because of how easy or how difficult it is to stimulate the system. So we have to meet back, right, at 1. Let's have a refreshment.